Started on the lesson, you'll notice that this chapter has a lot of little extension lessons that we kind of just put in to make them fit. So we're also going to talk today about symmetries of solids. We're going to describe planes of symmetry and axes of rotational symmetry of solids. Previously, we learned that a two-dimensional figure has line symmetry if it can be mapped onto itself by reflection in a line. And a two-dimensional figure has rotational symmetry if it can be mapped onto itself by rotation of 180 or less. We've actually learned that it's less than 180 degrees around the center of a figure. So a three-dimensional solid can also have symmetry. When a solid can be mapped onto itself by reflection in a plane, the plane is called a plane of symmetry. Makes sense. A solid can have more than one plane of symmetry. So for instance, going through a cube, a plane that passes through the midpoints of four parallel edges, and it could obviously have more than one plane of symmetry. A plane of symmetry for a solid, for a right cylinder, is going to be equidistant from the two bases. And for a right cone, it's a plane that contains the cone's vertex and a diameter of the base, so multiple planes there. Other planes of symmetry in solids in example 1 that have other planes of symmetry not shown above. For example, a plane that contains the diagonals of two parallel faces is also a plane of symmetry for a cube, as shown at right. For a rotation, a solid has rotational symmetry if it can be mapped onto itself by a rotation of 180 degrees or less about a line. The line is the axis of symmetry. Describe an axis of symmetry for the solid and a rotational figure that maps the solid onto itself. So a rectangular prism. The axis contains the center of two rectangular bases and it's a rotation of 180 degrees. The axis contains the vertex and the center of the base. This is a rotation of 120. And on this one, the axis contains the center of the circular bases, so it's a rotation at any angle. And there are going to be a few problems from these pages, or actually from this page, on your homework tonight. So today, lesson 11.9, exploring similar solids. We're going to use properties of similar solids. So first, for our warm-up exercises, find the surface area and volume of each solid. We have a right rectangular prism with side lengths of 8, 5, and 10. We need our calculator. So, for the volume of a rectangular prism, 8 times 5 times 10. Volume is 400. For the surface area, we're going to have two sides, two rectangles that are 8 by 5. So 8 times 5 is 40. We have two of those, which is 80. We're going to have two sides that measure 5 by 10. 10 times 5 is 50. Two of those is 100. And we'll have two that measure 8 by 10. 8 times 10 is 80. Two of those is 160. So 80 plus 100. And so I can add these all up. Equals a surface area of 340, a volume of 400. Now we have the right cone, which has a radius of 3 meters and a height of 4. So 3, first we're going to do the volume. 3 squared is 9. 9 times 3.14. The area that's circular bottom is 2.86. I'm going to leave this over here for when I do surface area. And then also the height is 4. Is 3.82. That's the volume. Now, surface area of a cone. We've always done surface area where you open it up and you have the shapes. But when you try and unroll a cone, you don't have a regular shape. So there is a formula for the surface area of a cone. And now we have a cone. So to find the volume of a cone, we've dealt with that. Volume is going to be fairly simple for us. So whoops, that'll make a mess. Let me clean that up. Okay, 3 squared is 9 times 3.14. So the area of that base is 28.26. I'll just put that over here because I'm going to need it for the surface area and I'm doing the volume first. Times the height is 113.04 divided by 3 because there's a pointy top. It's about 37.68. So I want to check that. 9 times 3.14 times 4 is that number. So 37.68. Now, for the surface area, this is where the standards get a little confusing. Surface area of a cone is actually not done in 7th grade. It's not done in 8th grade. And there's some debate about whether or not it's fair game on an EOC, whether or not you're expected to know that. So it's the formula for surface area of a cone is a little bit different because you can't just take this part here and unroll it into a shape we've already had, like you can for a cylinder. So what I did was I went online and found a lovely little site here that talks about surface area and volume formula for a cone. And I felt like it was really important to go through this, take a few minutes to go through this with you so that you understand where these formulas come from if you're expected to kind of come up with it. So a cone, as we know, is pyramid with a circular base and a side length. They're going to call, in this example, this is from a chemistry website, they're going to call this side length S. You will also see it called lateral side length sometimes, and it'll be a cursive L. So if you see that, that's what it is. So if you look at this, this side length is going to be equal to the square root of the radius plus the hypotenuse. So obviously you have a right triangle going on here. You use Pythagorean theorem to find that side length. So to then find the surface area of this cone, it is obviously the area of the circular base plus this unrolled piece here, which is not a regular shape, but is going to have an area of pi, 3.14, times the radius times this lateral side length. And I'm going to go ahead and clip this formula to go ahead and put it over here so that we can use this. So I would think they would give you this formula if they asked you to use it on an EOC. If not, hopefully you remember enough of what we're doing to remember it, or you memorize a formula, or you can at least kind of think about how you would get this. So as we said, the area of the circular base is 28.26. To get the area of this unrolled cone part here, you would do 3.14 times the radius. Now you need this side length, which I said sometimes you'll see written as a cursive L. So this is 3. This was a height of 4. So you might recognize, hopefully you recognize that 3, 4, 5 Pythagorean triple. Your slant light here is 5. So 5 times 3 is 15 times 3.14 is 47.1. 47.1, okay, plus the 28.26 that we already found was the area of the base. And my surface area of this cone is going to be 75.36. And my volume, remember from earlier, it was 37.68. Okay, so very close numbers there, obviously rounding issues because of a pi button. and find the surface area and volume of each solid. Now we're talking about a sphere. So we're back to formulas we know here. Hopefully remember surface area is equal to 4 pi radius squared. And volume is equal to 4/3 pi radius cubed. So I'm going to do surface area first. 7.3 times 7.3 is 53.29 times 3.14 times 4. And I'm going to just round this to the 10th is 669.3. So now we have 7.3 times 7.3 times 7.3 times 3.14 times 4 equals that number, and then we divide the whole total by 3, and the volume is 1,628.7. Okay, once again, close, difference being 3.14 versus a pi button. So now we get into the heart of the lesson, even though the warm-up took a little bit longer than normal because we dealt with surface area, of cones. But if two solids of the same type with equal ratios of corresponding linear measures such as height or radii are called similar solids. So basically we've dealt with similarity here before. There's going to be a common scale factor, a common ratio. The common ratio is called the scale factor of one solid to another. Any two cubes are similar, as well as any two spheres. So the green cylinders above cannot be similar because you can see right away that their heights are equal. So they have a ratio of 1 to 1, but obviously the circular bases do not have a ratio of 1 to 1. They tell us that the blue figures are similar. We haven't measured that out to verify, but we can see that they do at least appear from the drawing to be similar. So we're going to work this out now. We're going to identify similar solids. You guys can do this. We have this prism, and we can see that it's a square and a height. This isn't even a square on this side. This is 3 to 6, and you can see that these 2's correspond to the sides that are 3, and then the side length that's 4 would correspond to the side length of 6. 4, 6 reduces to 2/3. So they are similar with a scale factor of 2 to 3. They did a bunch of math there, but you can see the answer is similar to a scale factor of 2 to 3. Now explain if these are similar. Explain your reasoning. So from here to here, we can kind of see this 4 corresponds to 3. Okay, pen doesn't want to work. Oh, there we go. This 16 would correspond to 12, and this would simplify to 4/3. And the 12 would correspond to 9, which does simplify to 4/3. So they are similar with a scale ratio, of 4 to 3. And we'll wait for it to turn the page. Tell whether these solids are similar. So the radius 10 to 5, which reduces to 2 to 1, and 15 to 10 does not simplify to 2 to 1, so they are not similar. So now we have a similar solids theorem, and you can start doing this. This would making some comparisons, but basically, if two similar solids have a scale factor of A to B, then their corresponding areas are going to have a ratio of whatever A is squared to B is squared, because area is two-dimensional, and corresponding volumes will have a ratio of A to the third, B to the third, so that because the volume is three-dimensional. Makes some sense. So these cans shown are similar with a scale factor of 87 to 100. So we want to find the surface area and the volume of the larger can. So let's apply this. So if we take the surface area of can 1 over the surface area of can 2, that's A squared B squared. So 51.84, which is the surface area of can 1 over the surface area, which we don't know of can 2, 87 squared, 100 squared. And then the volume, do the same thing. The volume of can 1 is 28.27, and that's going to be equal to 87 to the third over 100 to the third as a ratio. We can go ahead and solve this. They don't go through much solving, so let's actually do this. So this is going to be 51.84 over x equals 87 squared is 7,569. 100 squared, it's going to be a 1 with 3/4, otherwise known as 10,000. So 10,000 times 51.84 is going to equal that number, equals 7,569x. So then we divide by 7,569, and we get x is 68.48. Then for volume, I'm getting a little tired of this black. So this is going to be 28.27 over x. 87 squared was 7,569. So I can take 7,569 times 87 and get 87 cubed. This is going to be 1. So 28.27 times 1, 2, 3. Okay, is going to be 2. Can't even read without the things here. So there'd be a dot there. So 28,270,000. I need my commas. It's 28,270,000 divided by 658,503. So about volume of about 42.9. So 68.49, 42.9. Okay, and there's our answers. Example 3, these pyramids are similar. Pyramid B has a volume of 1,000 cubic inches. And pyramid Q has a volume of 216. Find the scale factor. That's going to be A to the third, B to the third. In this case, both 216 and 1,000 are perfect cubes. 10 over 6, we always simplify, so the scale factor is 5/3. We can also use this concept when trying to figure out what's a better buy. So a store sells balls of yarn in 2 different sizes. The diameter of the large ball is twice the diameter of the smaller ball. If the balls of yarn cost $7.50 and $1.50 respectively, which ball of yarn is the better buy? So 1 is twice the diameter, even though we normally use radius. Still, the radius is going to be twice, so the diameter is twice cubed. So the larger ball of yarn should have a volume of 8 times more. Now, obviously, I don't really love this problem because it's yarn and there's some airspace in there, and one could be wound tighter or looser. You really would need to look at the label to figure out what the total volume is given on the ball of yarn, or you would have to look at each yarn will tell you how long it is. So it's not really a great real-world application, but you get the concept. What they're trying to get you to realize is that the larger ball of yarn has 8 times the volume. Once again, although yarn, you don't really deal with volume, you unroll it and you deal with length. But 8 times more should be $12, and the one that's 8 times more is $7.50, so it is a bet. So now we have cube C, which has a surface area of 54 square units. So 54 is going to be equal to some number squared. And cube D has a surface area of 150, which is going to be equal to some number squared. Okay, First thing we always want to do is simplify. I can see that 54 is divisible, not by 4, but it is divisible by 2, giving me 27. Okay? And 150 divided by 2 is 75. Okay? Now these are both divisible by 3. 27 divided by 3 is 9. And 75 divided by 3 is 25. And at this point, they're not, can't simplify them anymore, but they are both perfect squares. So if a squared is equal to 9, a is equal to 3. And if b squared is equal to 25, b is equal to 5. So the scale factor is 3 to 5. So the edge length of each of these, they wanted the edge length of just C is 3. And now we want the volume of D. So remember our scale factor, why is my pen not working now, is 3 to 5. D is the one on the bottom. 5 cubed is 125 square units. This is 125 square units. It should be 125 cubed units. Just caught that. What if, in example 4, calculate a new price of the ball of yarn so that neither ball would be a better buy? We'd actually already done that if you remember. We said $1.50 times 8 times larger is $12. And it's time for the daily homework quiz. 2 triangular prisms are similar with surface areas of 9 and 25. What is the scale factor? I feel like we just did this. 9 to 25, a squared to b squared because it's surface area, so that's 3 to 5. 2 spheres have volumes of 125 pi meters cubed and 216 pi meters cubed. What is the scale factor? So this is cubed and cubed, and the square root of 125, sorry, the cubed root of 125 is 5, the cubed root of 216 is 6. So what is the ratio of their surface areas? That would be 25 to 36. And 2 volumes of 2 similar square pyramids are 8 feet cubed and 27 feet cubed. What is the ratio of the surface area of the smaller to the larger? So 8 to 27 cubed means that the square root, sorry, the cubed root of 8 and the cubed root of 27. So that's 2 to 3. So the surface area of the smaller pyramid to the larger, 2 squared is 4, 3 squared is 9. And 2 solids are similar. Find the surface area and volume of solid 2. So their ratios are going to be similar. So everything is going to be doubled. So 2.5 over 5. So that's a scale factor of 1 to 2. Okay? So if I'm going to, I can actually go ahead, I'm going to do this a few different ways. I'm going to actually use this to find this is 12. And since they just want the solid surface area, I'm going to use this factor, and I'm just going to go ahead and solve. So for volume, this is a hemisphere. So the formula for volume for the hemisphere, instead of 4/3, is going to be 2/3 pi radius cubed. 5 times 5 times 5 is 125. Times 3.14 times 2 divided by 3. So the volume of the hemisphere on top is 261.7. The volume of the cone is 25 times 3.14. So the area of the circle, because I'm going to need that for the surface area. Oh, I'm not going to need that for the surface area because that's not an outside surface. So 78.5 times 12 divided by 3 is 314. I'm just going to double check that because I got sidetracked and I'm not sure if I did it all. Okay, so the volume, I'm going to add these two up. So I'm going to put it in a different color, so I'm going to erase it by accident. 261.7 plus 3, I didn't want to do that. 261.7 plus 314 equals the volume of the second solid is 575.7. Now to do the surface area. In order to do this, I want to clean up some work here. Because for the surface area, I don't need the surface area of the base of the cone. Back to red here. So half of the area of a sphere, so the volume instead of being 4 would be 2, and that's not volume, it's surface area. Volume equals 2 times pi times radius squared. So 25 times 3.14 times 2, because it's only half of a hemisphere, half of a sphere, so it's a hemisphere. So that surface area of the hemisphere is 157. Now, even if you don't remember quite the formula to find the surface area of this, you might remember that you have to find that lateral length. So let's first do that. Remember that you have to find the lateral length. So 25, because 5 squared, plus 144 equals 169. The square root of 169 is 13, and some of you are probably yelling at the screen saying, Mrs. Falk, Pythagorean triple, but maybe you didn't remember that. So let's think about this formula. It was originally the area of the base plus, it was pi times the radius times this lateral length to find that volume. So it was 3.14 times 5 times 13 equals 204.1. So if I add the 204.1 plus the 157, I get a surface area of about 361.1. Because of the pi button, these answers are going to round slightly, but looks good on surface area and looks really good on volume. A lot of work there, but we were able to get through it and do it. And then here are the pages that your homework comes from.